In this video, we're going to be talking about noise in electrical circuits. Noise is something that we obviously don't want to have. In this video, I'm going to talk about various sources of noise that can affect electrical circuits, how they can be modeled, and how they can be defined. First of all, let's look at a graph of what you might expect to get if you measure a noisy circuit. If you've ever taken an oscilloscope and used it to measure a noisy circuit or a circuit where the power is not yet turned on, this is what you're likely to see. Noise by its very nature is random. This graph is just a simulation of what noise might look like. If you look at the size of my axis here, 0.1 volt at the maximum amplitude, we can say, wow, this is really a noisy measurement right here. Something we can say about noise, though, in general, is that it tends to be an AC phenomenon. Look here at the average. The average voltage due to noise tends to be 0. I mentioned that noise is something that we don't want to have in a circuit. Let's now think about what would happen if we had a very clean signal somewhere in our circuit. Here I'm showing a sine wave. This is what we hope to measure, say, at the output side of an amplifier if this started out to be a very small signal. Sometimes, though, when we build electrical circuits and actually do measurements, we see something more like this. What I'm plotting right now is just the addition of the noise that we see on the top to the nice signal that we saw just a moment ago. What causes noise in electrical circuits? Well, I'd like to draw your attention to 3 primary causes of noise, and I'll elaborate on them in a little bit more detail. The first source of noise, and it's probably the primary source of noise in electronics, is thermal noise. Anytime you have something at a temperature higher than absolute 0, you have movement. Electrons move around in conductors. Let's now imagine that we have a horizontal section of wire and we have electrons moving around randomly in that conductor. Let's consider a single cross-section of the conductor. If we don't have the wire hooked up to any power source, then the electrons are just going to be moving randomly, and the amount of randomness or the amount of movement that each electron has will be related to the temperature. At any given moment in time, you're going to have some electrons moving from left to right and some electrons moving from right to left. Again, through this cross-section, we sometimes might have more electrons moving in one direction than the other. That would show up as a current flow. If I consider that current with respect to time, sometimes I'm going to have a positive current and sometimes I'm going to have a negative current. Since thermal noise is random by its very nature, we're going to get a plot of the current very similar to the plot we have of the voltage on the left. The average current is 0, but the RMS current will not be 0. In other words, there's power in that wire, power that's being dissipated, but there's also a source of power externally because the wire is heated by its environment. The second type of noise is probably less common in ordinary electronics, and it's called shot noise. Shot noise is related to the quantum mechanical or discrete nature of charge, that is, the electron. 1 coulomb is defined as 6.24 times 10 to the power 18. So 1 ampere of current represents a huge amount of electrons flowing through a circuit. But imagine that we wanted to measure a flow of current that is very, very small, say 10 to minus 18 amperes. Well, that represents somewhere in the neighborhood of 1 electron per second on average passing through a cross-section of the conductor. Of course, when you actually go to measure that current, it's not 1 electron per second. Boom, boom, boom. It has a random sort of a nature to it. Boom, 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 boom. Something along those lines. So you can see that if you try to measure current at a very small scale, that measurement is going to be a little bit noisy. And that noise is called shot noise. We'll talk about shot noise a little bit more in a future video. The third type of noise that I'd like to consider is external noise. And I'm using the word external to represent many different types of noise that can affect an electronic circuit. One example of external noise, for example, could be radio waves. Anytime you have a wire and you have radio waves in the environment floating around, that wire can absorb some of the radio waves. A radio wave then causes electrons inside of the conductor to move back and forth in sync with the radio wave. So electromagnetic interference, in other words, is a source of noise in an electrical circuit. Also, anytime you're in an electrical circuit, you have noise coming from other components that are nearby inside the circuit, and I'm calling that here also external noise. I'd now like to consider how you might be able to model noise in a circuit. This is a little bit tricky because quite often the source of noise is external to the circuit itself, yet we need to somehow represent that mathematically as being within the circuit. Even for thermal noise, we don't often have a convenient way to represent that noise. What I'm going to do right now is to simply represent the noise as a voltage source. That is, it's a source of power. In the case of thermal noise, that power is coming from the thermal bath in which the circuit sits. On the other hand, since we have a source of power, we also have to somehow dissipate that power. So I'm going to include a resistor here in our model. We'll call it a noiseless resistor because taken together, this little source of power and our noiseless resistor can be considered just a simple section of conductor that has a particular resistance. Now the resistor here is important because without a resistor, you have no way to dissipate power and you're not going to have any noise. Consider, for example, a length of a superconducting wire sitting near absolute zero. If I launch an electron down that superconductor, the electron's just going to carry on moving at whatever initial velocity I give it. The electron's not going to impact other electrons, it's not going to change direction, and it's not going to scatter around. If an electron doesn't change direction, we're not going to have this AC current flow that's typical of noise, like what we're plotting here. For these reasons, it's necessary to have a resistor inside the circuit fragment. So we have a source of power and we have a way to dissipate that power. And at thermodynamic equilibrium, of course, these two have to be the same. If I were to take this circuit fragment and hook it up to an oscilloscope and measure the voltage across the two sides of the circuit, I would get some plot like what we're seeing here on the right, voltage versus time. The average voltage due to the noise is 0. However, because this is something like an AC signal, we are going to have an RMS voltage. That RMS voltage, in a sense, represents the amount of power that's circulating around inside the circuit fragment. At any given moment in time, there's a particular probability of having a voltage measured that's unequal to 0. For example, at this instant in time, we have a particular voltage, but at some other instant in time, we have 0 voltage, or some higher voltage, or an even higher voltage. But it's impossible to predict at any given moment in time what the voltage due to the noise is because noise is inherently random. What we can do, though, is define an RMS voltage, or a sort of an average. We can also talk about the noise probability density. That is to say, how probable is it at any given moment in time to have a particular voltage measured that's due to the noise. Let's make a little plot of what the probability density is of our noise that we already have pictured here on the right. On the vertical axis, I'm plotting probability density, and on the horizontal axis, I'm plotting voltage. The most probable voltage is 0. Looking back at our plot, it's centered around 0. As the voltage gets higher and higher, or as the voltage gets lower and lower, it becomes less probable to find a signal at that voltage. For example, way down here at minus 0.15, we're off of the chart. I don't see any signal at all down here. That's why down here at minus 0.15, we don't see any voltage in our plot of probability density. On the other hand, here at minus 0.5 volts, it's more probable than it was at a lower voltage. For different types of noise, we might have different noise probability density functions. In other words, the way that function looks might depend on the source of the noise. We can also consider the spectrum of the noise. In other words, what is the intensity versus frequency? If I were to take this voltage versus time graph showing the random noise that we already have shown here in the view graph, would we have more noise at the high frequencies or would we have more noise at the low frequencies? If it's white noise, then we ought to have equal amounts of noise at both high and low frequencies. However, if we have some other source of the noise, then we might have more noise at one frequency than some other region of the graph. White noise would look like this, where the intensity is relatively constant over a very broad range of frequencies. Eventually, the intensity of white noise does have to fall off when the frequency gets high enough. If that were not the case, then you could find the power circulating in the circuit by integrating the intensity over frequencies from 0 to infinity, and you would calculate that we have an infinite amount of power circulating in the circuit, and that's physically impossible. So even white noise has to eventually fall off to 0 if the frequency is high enough.